on the assumption that the costs are positive, right? So if there is any edge whose cost is negative, then this algorithm doesn't work. Okay? So something you should remember, because there are more other shortest path algorithms which work with negative weights and so on. Okay? Of course, remember that if a graph has a cycle which has negative cost, then the whole shortest path problem is meaningless, because you can keep going around in cycles and get lower and lower cost. So basically, the least cost path in such a graph will always be minus infinity, right? So it's not a meaningful formulation. So we only talk about graphs without negative cost cycles whenever we talk about shortest path. Okay? And there, if there are even if there is a single edge that has negative cost, then you cannot generally use Dijkstra's algorithm. You have to use something else. Okay? There is an algorithm called Bellman-Ford, which again we'll talk about in a few lectures, which you can use to do this. Okay, so that's brings us to the last application that we are going to consider in greedy algorithms. Okay? And this is Huffman coding is what we're going to talk about. But before we go into that, it's useful to have a little bit of a background in information theory, right? So information theory talks about information content of an event. Okay? So if an event occurs with a certain probability, then you say its information content is given by minus log p. Okay? Now, what does that mean? Okay? So the idea is that the information contained in an event is, in a sense, dependent on the surprise factor, right? So if I tell you that the sun rises in the east, right, I might as well not have said anything to you, right? Because I'm not conveying any useful information. It's something that everybody knew, right? So that's why an event that's almost always likely conveys no information. So if you take, if the probability is 1, then minus log 1 will be 0, right? On the other hand, if it occurs with a very, very low probability, then log p will be a large negative number, and so minus log p will become a large positive number, right? So essentially what it says is that a rare event carries a lot of information, and a frequently occurring event carries no information. Okay? Then information content adds up, right? So if there are two events, E1 and E2, then their combined information content is, the sum of their information contents, right? Does that make sense to you? Why does it make sense to you? Right, that's why, right? So if E1 occurs with the probability P1 and E2 occurs with the probability P2, the likelihood that the two occur is, assuming in independent events and so on, right, is P1 times P2, and then if you take the information content of that event combination, it will be minus of log P1 P2, right, which reduces to minus log P1 plus minus log P2, right? So it's not magic. It is an observation that information content tends to add up, right? It's not a definition, right? Whereas this is something you can think of as a definition of what it means, how we are defining information content. So there is this concept of entropy, right? In information theory, there's a concept of entropy. So the entropy is nothing but the expectation over the information content. Okay, so a high entropy means, there is a lot of information being carried. A low entropy means there isn't a lot of information. Okay, so so we use the notation H to talk about entropy, right? And it's given by the expectation, or think of it as a weighted average. So expectation on x, and because x is can take value xi with probability pi, then essentially information contained in x is obtained by taking essentially the weighted sum, right? So with the probability pi, right, xi is going to appear, right? And xi's information content is minus log pi, right? So the message x could be x1 with the probability p1, x2 with the probability p2, x3 with the probability p3, and so on, right? So we are trying to combine the, compute the average, right? The weighted average where the weighting is based on the probability, right? So with the probability p1, x1 will occur, and in that case we have minus log pi as the information content, right? With the probability p2, x2 will occur, and its information content is log p2, and so on, right? So if you take the average of all of this, then that'll give you the average entropy for this variable x. Okay. So it plays a fundamental role in coding, and that's why we are talking about it. So there is a famous theorem by Claude Shannon, right? So this is a you hear about Turing all the time, right? So Alan Turing, when you are a computer scientist, you must have heard about Alan Turing. And Claude Shannon is is a equally famous name, right? So maybe not for every programmer, but in terms of how fundamental this theorem was, he's been every bit as influential. So what it says is that there's this fundamental theorem that says that if you have a random variable x, right? You can think of it as a message that you want to encode, let's say, right? Because the message is at some level, it is a variable, and it's a variable whose value is constructed, over an alphabet consisting of certain characters. What it basically says is that this variable cannot be encoded in fewer than h of x bits. Okay? And interestingly, it can also be encoded using h of x plus 1, right? I mean, you can imagine that you obviously cannot do any better, because if this one gives you a number which is 7.2, right? You cannot actually have a 7.2 bits, right? So you have to round it up, right? So that's why it says that you have to the actual limit that you can achieve is up to one number larger than what is the least achievable. Okay, so essentially what the first part is saying is that it's like this, sorting lower bound that we established, right? So we said, I don't care how you do the sorting, but as long as you're only using comparisons, you cannot do sorting in less than n log n time, right? So this is even more general result, because it says, I don't care how you encode, right? Regardless of what encoding technique you use, you can never encode that message in fewer than h of x bits. Okay, so that's a very, very impressive theorem. And if you look up the Wikipedia, you'll find that actually there's a very simple proof, right? So I'm not going to go through that, but you can. Those of you who are interested, I encourage you to look at it, because when I say simple, I don't mean, given the fundamental nature of this theorem, it's simple relative to that. No, it's actually quite simple, and some of the summations that we have proved in class, they are more complex than the justification for this. So I encourage you to go and look at it. So now, as computer scientists, we are interested in bounds, but we really want to know how to do this, right? So how do we encode this using this many bits? And Huffman coding is an algorithm for achieving that bound. Okay, so how do we achieve that? We are going to just, describe the algorithm in text, right? So we're not going to give you any pseudocode, okay? The algorithm is quite simple. So let's illustrate with an example, right? Let's say sigma, your alphabet consists of 4 letters, A, B, C, D, right? And let's say they have probabilities of 0.55, 0.02, 0.15, 0.28, right? So essentially what you're saying is that if you have code words or sentences, then in those sentences, the letter A occurs with a probability 0.55. That is, essentially every other character in your message is going to be an A, right? And whereas only every 50th character is going to be a B, right? And so on, right? So if you use a fixed length code, which is sort of what we would use by default, there are 4 characters to code, so you need at least 2 bits if you use fixed length encoding. Okay? Alternatively, you can use a variable length code, and if you go back to our information theory, and we simply say, okay, how much ever information content is there, I will use that many bits. Okay? So I'm going to use 1 bit for A, right? And because 1 bit can capture 2 values, right? So so I'm going to need B has a lot of information content, so for I'm going to use so if you think about log, right? So we are talking about log in the binary sense. So minus log 0.55 is actually going to be what? 2, right? So this is minus log, it's going to be 1, right? Because mine approximated to log 0.5, right? So that is log of 2 to the power minus 1. So obviously it's going to be mine. So this one reduces to minus 1, minus of that is 1, right? So that's how you get from probability 0.5, you get that you can encode it using 1 bit. Okay. Similarly, you do that on B. On B, you'll see that it's 2 by 100, right? The closest approximation is 1 by 64, right? 1 by 64 requires 6 bits, right? So that's what it is. Right? So C, 0.15, 1/7, its closest is 1/8, so 3 bits. Similarly, 0.28, closest is 0.25 and 2 bits, right? So now you compute the entropy, right, or the weighted average for across this. So you get, so with the 0.55 probability, I'm going to have an A, right? In which case I'm going to use only 1 bit. With 0.02 probability, I'm going to use a B, which is encoded using 6 bits. So the expected length of the message is going to be this weighted sum, and that is 1.68 bits, right? Which obviously is better than 2 bits, right? So the lower bound, if you just apply the entropy, is going to be actually somewhat different, and I don't know why I used slightly different values here than what I have indicated there. Okay, but you can substitute exactly those values, and what you will find is that the number is quite close to this. And what that says is that, okay, the actual achieved is pretty close to the lower bound, right? So we are doing pretty well. So now this is sort of an example that shows how we could assign number of bits, but now we still haven't said, how the numbers are going to be encoding. Just saying that give 1 bit to A and 6 bits to B doesn't tell us exactly what the code is, right? So that's what we're going to try to specify in the next slide. Okay? So this is how we are going to, this is an example, right? So A is going to be assigned the code 0, B is going to be assigned the code 1, 0, 0. Okay? And so you can see that actually what happens is that although you assigned B 6 bits, you don't really need 6 bits. Okay? So what is this tree? So what this tree is depicting is something called a prefix code, right? So it's a form of variable length coding, right? And it should have this prefix property, that is, no code should be a prefix of another code, right? Because if, let's say, A happens to be a prefix of D, then after you have seen up to the end of A, you're not sure whether you're seeing an A or you should just continue to see more symbols until you get to the end of D, right? So that's why the prefixes should diverge at some point, okay? So when the prefixes diverge, then you can construct something like a automata or tree data structure, right? Or a decision tree data structure, where based on the value you go either left or right, right? If the first bit is 0, then you're going to go down here, and then you reach a leaf, so you already have a character A. If the first bit is 1, you're going to come down here, then you're going to look at the second bit, let's say that is 1, then you're going to come down on the right branch, and you get to D, right? And so on, right? So this tree represents a prefix code for encoding A, B, C, and D, right? So you can see that because already you reach a unique place, you don't need to assign more bits. So actually you can do with assigning 1 bit to A, 2 bits to D, and 3 bits to B and C. Okay? So the average coding size actually is 1.62 and not the 1.68 we calculated, right? So what the information content allows us to do is to assign a number of bits based on the probability, but we may be able to do slightly better than that, okay? And then, so in particular, right, what happened was that So in particular, the information content gave us the right number of bits for A, C, and D. For B, it assigned an excessive number of bits, and we realized that no, you don't need that many bits, you can just chop off at 3. Okay, so now, we have the background, and we can talk about how the Huffman encoding technique works. Okay, and the algorithm is exceptionally simple, right? So what you do is somebody gives you the characters and the probability of their occurrence, right? Or rather, you can think of them as frequencies, right? So probability is inversely proportional to frequency, right? So something that occurs very infrequently, right, is going to have low probability. Did I say
directly? Frequency is probability.
Right. Okay. Yeah. So I misspoke. So frequency is directly proportional to probability, and therefore, we are going to build this. We are going to compute this frequencies, and so instead of talking about probabilities, we are simply going to talk about frequencies, because what matters really is the ordering between the probabilities, not the probabilities themselves. Okay? So, we have characters and their frequencies, and then what we do is we take the 2 characters that occur with the minimum frequency. Okay? So, let's say these are the two characters, right? So we put them as leaves of a 3-node tree, okay? And then here, what we do is, whenever we reach this node, right? We reach this node F1 plus F2 times, right? Because we're going to come to this node through this node, and we are going to come to this node through this node. And if you're going to visit this leaf F1 times and this leaf F2 times, then the ancestor needs to be visited F1 plus F2 times, right? So for the purposes of deciding how many bits to assign to this node, we can use the frequency F1 plus F2, right? Because that's how often you're going to visit this, right? So we do that. Now, what we have done is we have taken the two least frequencies, we have constructed this node, then we delete these two characters, and we pretend that there is another new character which has frequency F1 plus F2, right? So now we have a new instance of the problem where instead of having 5 symbols, right, we have 4 symbols, right, with these 4 frequencies, right? And then we take which ones have the lowest, right? Let's say F3 and F4 do, then we go up and we construct that, and we keep repeating this. Okay? So it's a simple recursive technique where at each step you take the 2 least frequently occurring alphabets, right? And then you connect them together and then replace them with the combined frequency, and then just keep repeating. So what is its complexity? So there are, let's say, n characters, right? So what is how fast can this algorithm be?
Log n, where
N log n, right?
log n,
Right. So obviously you have to assign a code to every
level.
character, right? So this means the way this algorithm works, it just reduces the number of symbols by 1, right? So it takes these 2 and combines them into 1 symbol, right? So each iteration reduces the number of symbols by 1. Therefore, the recursion is going to be repeated n times, and each time you want the 2 minimum, right? And therefore, that could be up to log n time if you use a priority queue for cost, then it's going to be up to each step could take log n time, so totally it could be n log n, right? Okay, very good. So that's the Huffman encoding, and once again, it is a greedy algorithm because it's just, it's really saying I don't care about all of them, right? There is no global optimization being done. It just looks at the 2 least frequently occurring things, and then it does something, and then it just keeps doing that simple, it makes that simple local choice at each step, right? So that's why it is a greedy algorithm, right? Now, how do we show that this is, we'll come back to that. So this is an example, right? So here is a sample sentence, right? Now, what is special about the sentence?
It has all the alphabets.
No, it describes itself,
Yeah.
right? The sentence contains 3 A's, 3 C's, 2 D's, and so on. It describes
Right.
the distribution of characters in the sentence itself, right? So it's a self-referential sentence. Okay, so if you use Huffman encoding, you get this tree, and it uses about 650 bits as opposed to 850 bits for a fixed length code. So for instance, if we're talking about alphabet A through Z, so there are 26 letters. So if you use a fixed length encoding, you'll need 5 bits, right? Because 32 values right? 32 is the power of 2, that's bigger than 26, so you need 5 bits. If you use the fixed length code, you'll have 8050 bits, otherwise you'll have 650 bits. Now, so the optimality is based on, again, the greedy choice property, and we have we'll use the same exchange argument, right? Suppose the optimal prefix tree does not use the longest path for 2 least frequent code words, right? Then what you will show is that, okay, so let's say this is the prefix tree, right? And let's say here is C1, and here is some C prime, right? So this, let's say this is A, this is B. Let's say A is the least frequently occurring character, right? Sorry, let's say B is the least frequently occurring character, okay? And so that means we'll give this F1 and we'll give this F2. So let's say that somehow the optimal code happens to be one in which B has fewer bits than A, right? So notice that F1 less than F2, but code length for B is less than code length of A. So in that case, what we are going to do is, let's look at the parent of A, right? And the parent of B. Okay? So what you can do is, you can just simply swap A and B between these two, right? So now the new cost, right, will be given by so the original cost was something like length of B times F1 plus length of, let's just call this, let's call this L1, right? This is L1, L2, right? So let's, instead of writing this long code length whatever thing, right? So we just say F1 is less than F2, but L1 is less than L2, right? So in that case, the original weighted sum would have included L1 F1 plus L2 F2, right? So whereas we would now have something like L1 F2 plus L2 F1, okay? And you can easily show that this is actually I suppose you'll be able to see it only if you express L1 as some. I think you'll see this only if you express Okay, so I suppose I'll have to do more arithmetic to show you that in fact this is smaller, but instead of trying to do that here, I will just move on to the next step, and I'll update the slides to show you that in fact it is smaller. Okay, so
So we should just show the log, of f1, f2, and if like log of it. I mean, we're just basically trying to calculate the entropy. So
no, it doesn't matter. This calculation should give you the answer, right? Somehow, if I tell you, right, intuitively it is obvious that if I do the switch, right, now I'm going to, have a smaller weighted length because